samples. I'll wash them and then put them in the drying oven. So it's not going to take too much time. It was brought to my attention that the Excel app on the El Camino Outlook, or Microsoft Office 365, doesn't have the add data function. So since that's the case, here if I wanted to add or format data, I can't. We're going to go back into the computer lab today to finish up some of the plots. So we'll do that after we do it. It shouldn't. Hopefully, you don't have a clogged crucible. So what you should do is before you start filtering, well, you'll see this when you pour the supernatant in here. You'll see how fast the flow rate is. Make sure you don't get any precipitate in there, or you can just put some DI water in there to make sure that the flow rate is reasonable. If the flow rate is very slow, then you might see about switching the crucible. Otherwise, it's going to take too much time to filter your samples. All right, so we need to generate the plots here. I think the full version of Excel, and you used to be able to download the full version of Excel off Office 365, but I was looking here. It looks like it's just web-based apps. And let's look at the calculations that we're going to do for our experiment 2. And so the first plot we had generated is the temperature versus the time. And what we're interested in is the temperatures at 6 minutes. In fact, those are the only temperatures we're interested in. The problem is we don't have all the temperatures at 6 minutes. So what we need is we need the hot water temperature at 6 minutes. We need the cold water temperature at 6 minutes. And if it could mix in one instant of time, we need the mixture temperature at 6 minutes. And so we can't mix these in a microsecond. It takes time to mix them. And during that time, the hot water is going to continue cooling down. So, right at the time that is 6 minutes, the time we chose here, what would the temperature have been? And so we're going to get the equation for this and solve for y at x equals 6 minutes. And we'll do the same thing for the cold water. The cold water would be a little easier to predict, but we want the temperature y when x is 6 minutes here. Now the mix, if you have warm water, it's not going to heat up naturally. It should be cooling. So this is incomplete mixing. So this is why we ignore the initial points and just focus on the latter points of the graph, because by 8 minutes or longer, it should be well mixed by then. And assuming it was well mixed up here, what would the cooling curve have been? And so this would be the T mix. So we can label these T hot at 6 minutes, T cold at 6 minutes, and T mix at 6 minutes. And so I just labeled TH, TM, TC. Now, what we did was we poured the cold water into the hot water. Is that correct? So we poured the cold water into the hot water. So what's going to happen in that case? What's going to happen is the cold water is going to warm up and the hot water is going to cool down. And that's going to be our mixture temperature. But it's not just the hot water that's going to cool down, because the styrofoam cup that's in contact with the hot water will also cool down. And so we assume that the styrofoam cup is in thermal equilibrium thermal equilibrium with the hot water. So we say that the cup, even though the cup outside doesn't feel hot, you know, it's at that temperature where the hot water and the cup are at the same temperature, at least internally here. And so what we're going to say is, in this particular case, we're taking 50.0 milliliters and 50.0 milliliters here. And then when we combine them, we're going to end up with 100 milliliters total. And so the 50 milliliters that were cold are going to warm up, and the 50 milliliters that were hot will cool down. And so we end up with 100 milliliters. Now, in this case, there's no volume change, because we started initially with a volume of 100 milliliters, and we end up with a volume of 100 milliliters. So the only energy exchange is in the form of heat, not heat and work. And so we can just use this form of the first law of thermodynamics, so that is the Q of the system is equal to minus Q of the surroundings. It doesn't matter which one you call the system or surroundings. Which one do you want to call the system? Maybe we'll call the cold water the system. And so what we're going to say is Q of the cold water is equal to the system. However, the surroundings is not just the hot water, because not only is the hot water going to cool down, what else did I say was going to cool down? The cup. Now the cup is what we call the calorimeter, because the cup consists of the styrofoam, the lid, the probe, you know, because the probe initially was at a hot temperature as well. And so when we pour the cold water in there, all this is going to cool down, including the air in here, which is humid air, and even the air outside here cool down. And so the surroundings is a bit more complex, because what we have is we're going to have the hot water plus the cup plus the probe plus the lid plus the air plus the rest of the universe. These are all objects. You know, this is not a reaction or process. And so we just have all these objects. The situation with these objects is we're going to collectively call these, everything past the water, the calorimeter. And we're going to call the whole assembly the calorimeter, the probe, the cup, the lid, the air, everything's going to be the calorimeter. And so what we're going to do is we're going to determine how much heat was lost by the calorimeter in addition to the hot water. And so Q of the cold water is going to equal minus Q of the hot water plus any heat that's lost by the calorimeter. So we have the equations for an object. Q of an object is equal to what?
The heat of an object.
Yeah, the heat gained or lost by the object. And so Q of the object, was there an equation for it? Well, a lot of people will say Q is equal to MC delta T. And so if we say Q is equal to MC delta T, where M is what?
Mass.
The mass. Do I want to weigh the cup, the probe, the lid, the air, and the rest of the universe? No, we're not going to weigh it. And so I'm not going to use this particular one. I'm going to say a more general. This is more specific.
Let's do it.
I'm just going to call it the amount times C times delta T. And the amount of calorimeters I have is just 1. But the amount of water I have is 50 milliliters. Okay. And so what I'm going to do is I'm going to do this. Q of the cold water, what is that equal to? Q of the cold water is equal to the amount of cold water. It should be in grams though. 50.0 milliliters is how many grams of water?
50.
Yeah, so we'll just convert it straight. That's 50.0 grams of water times C. A lot of people have the specific heat of of water memorized. It's 4.18 joules per gram degree C times delta T. Delta T is T initial, not T initial, T final. T final is the mixed minus T initial. The cold water is going to be T sub C, temperature of the cold. These we're going to get from our graph
Question.
at 6 minutes. All right, this whole thing is going to equal minus Q of the hot plus Q of the calorimeter. Q of the hot water is just another object, and so the hot water is just going to be 50 grams of hot water times C, 4.18 joules per gram degree C, times delta T. Now the hot water has a different delta T. The T final will be the same. It's just going to be the mix, but the T initial is T hot. All right, plus Q of the calorimeter. How many calorimeters do we have? Just one calorimeter. So this is just going to be C of the calorimeter. I don't know what C of the calorimeter is, times delta T of the calorimeter. Delta T of the calorimeter, it started in thermal equilibrium with the hot water
So
and ends at thermal equilibrium with the mix. This is the mix here. And so it's going to be T mix minus T hot. And so the only unknown here is C of the calorimeter. And so the whole purpose of the first experiment is to determine how much heat is lost through the coffee cup calorimeter. We want the heat capacity of the calorimeter in this case. So in terms of what we often do with energy is write these in terms of an energy level diagram. In terms of an energy level diagram, the cold water is going to warm up. So we're going to have 50.0 milliliters of H2O liquid at T cold. And this is going to warm up to 50.0 milliliters of H2O liquid at T mix. And then the hot water and the calorimeter will cool down. So we're going to have 50.0 milliliters of H2O at T hot plus 1 calorimeter at T hot. Okay, and then this is going to cool down here to 50.0 milliliters of H2O liquid at T mix plus 1 calorimeter at T mix. It's T hot and T hot here. And so any heat that was gained by our system here had to have come from the surroundings over here. So Q of the system over here is equal to minus Q of the surroundings. Here. So the surroundings are going to lose energy here. The system's going to gain the energy here. So that's what we have here. And we can make these equal by changing the sign. So Q of the system is equal to minus Q of the surroundings. What was the next experiment that we did?
NaOH plus HCl.
Solid NaOH plus HCl?
Aqueous NaOH plus HCl.
Oh, aqueous. Okay. So what we did was we did HCl plus NaOH. What were the molarities of the HCl and the NaOH?
1.05 molarity for HCl and 1.00 molarity for NaOH.
Okay, 1.05 molar and 1.00 molar. And how many milliliters of each did you use?
Right, 50 and 50.
50 and 50?
Yeah.
Can you tell which one's the limiting reagent?
Yeah.
Which one's the limiting reagent?
Smallest molarity.
Yeah, sodium hydroxide. It's going to be the limiting reagent. When we do milliliters times molarity, we have millimoles. So this is 50 millimoles. Of sodium hydroxide. Whereas over here, this is going to be like a little bit higher.
Like 50.025.
Okay.
Give or take.
Yeah. 50 point, all right. 50.25, is that it?
Yeah, 52.
And so this is going to be an excess reagent. This is going to be our limiting reagent here. And so we're going to have 50.0 millimoles of reaction. These react in a 1-to-1 mole ratio from sodium chloride and water plus heat, energy. All right, so if I take my HCl and my sodium hydroxide and mix those together, how many milliliters of product solution will I end up with? 100 milliliters. So this is 50, this is 50, so my initial volume was 100, and my final volume is going to be 100. Is any work done?
No.
No. No work. And so we're going to do this. Now, the HCl and the sodium hydroxide are going to be at the same temperature or close to the same temperature. They might be slightly off. The reason they might be slightly off is because the probes, calibrations, aren't synced. That is, one probe is reading a little high or a little low, and so the two probes aren't synced. If that's the case, you're going to get two lines here, but that's all right. One or two lines. Right. Let's just say my probes are slightly out of sync here. Okay, when you mix them together, what happened to the temperature?
It drops.
Well, these are kind of already at room temperature.
It became hotter than the original too.
Okay. Actually, the temperature should have increased, I think, and then started to cool down. And so we do the same thing here. We're going to get the temperatures at 6 minutes. And so we'll solve the equations. We're going to get T mix, and the T of the HCl, and the T of the NaOH. Here. Since we're taking 50 milliliters and 50 milliliters, what we're going to do is we're just going to average it. If your two temperatures aren't the same, we're going to figure out what they are at 6 minutes and then average those two. So that will be our T initial. All right, this in this experiment, it's going to be a little bit different. In this case, our system, I'm going to call this. Our system is going to be the chemical reaction, HCl aqueous plus NaOH aqueous. And we're going to have 50 millimoles worth of reaction here, not 1 mole. And then this is going to produce NaCl aqueous plus H2O liquid. Was there any work done? I think I asked you that before, but was there any work done?
No.
No. There was no work done, and so all that energy is going to be exchanged in the form of heat. You know, because energy is exchanged, the first law of thermodynamics says that the energy is going to be exchanged in the form of heat and or work. So in this case, we have Q, but this is not an object, this is a reaction. So Q of the reaction or process is equal to what? Q of a reaction, this is for the intensive, or no, intensive is usually written delta U. Q of the reaction is usually extensive, so it's going to depend on the amount. We don't have that much reaction happening, only 50 millimoles worth of reaction occurring. And so it's going to be the amount times delta U, whereas delta U is usually per mole. We don't have a full mole of sodium hydroxide reacting here. We just have a fraction of a mole reacting. And so the Q is equal to the amount times delta U. Well, I could try to look up delta U, but yesterday was kind of a hassle to find that delta U. But it was also a hassle to actually do this experiment. And so I don't know which one was more of a hassle, probably doing the experiment. And so what we're going to do is, we know that this is our system here. So Q of the system is going to equal Q of the reaction, which is going to equal the amount times delta U. And we're going to set this equal to minus Q of the surroundings. So all that heat that was lost in this reaction, all that energy that was generated, goes into the surroundings. Now, what is the surroundings here? What do my surroundings consist of?
The universe.
Yeah, that's it. But at the initial level, we're going to have the product solution. That is, we're going to have 100.0 milliliters of sodium chloride solution that's left over. And even though you go, isn't that part of the system? No, it's not part of the system. The system's the reaction. Once the reaction's done, then the system disappears, and we're just left with surroundings. And so once this reaction's over with, there's no more reaction left. And we're left over with the surroundings. The surroundings are going to be the product solution, 100.0 milliliters of sodium chloride. And so that's going to warm up. And so all that energy that we get from this chemical reaction goes into warming up this sodium chloride, this salt water that I have left over here. Salt water plus a little bit of excess HCl. Just a tiny bit of excess HCl. Does it go into warming up anything else? The cup. The cup, the lid, the probe, the air, which we call that all the rest of the universe. In other words, we're going to have 100.0 milliliters of sodium chloride plus the calorimeter. We're going to call that whole assembly the calorimeter. And this is going to be at T initial, or T cold, if you want to call it. This is going to be T initial. The T mix here at 6 minutes will be the T final. So T final is equal to the mixture temperature here. And so what's going to happen is this is going to warm up from the initial temperature up to the final temperature here. And so all that heat goes into warming up the product solution and the calorimeter. Well, how much heat is that going to take? Well, we can calculate that. We need to know the amount of product solution. We do know it. It's 100.0 milliliters. But do we know the specific heat of the sodium chloride solution? Actually, we could look it up. I mean, I could figure out what the molarity is and then look up the specific heat of the sodium chloride. But you know what I'm going to find? The specific heat of the sodium chloride, since it's not that concentrated, it's going to be about 1 molar. Well, 1 molar is starting to get concentrated. It was 0.1 molar. It wouldn't. It's going to be off a little bit. But what we're going to do is we're going to make a couple of assumptions in doing this. The Q of the surroundings is going to equal minus Q of the sodium chloride aqueous solution plus Q of the calorimeter. These are the assumptions we're going to make. The first assumption is, I don't even know what the density of this is. You know, I know the density of water, and so that's why it was so easy. You know, if I had 50 milliliters, I'd just call it 50 grams. That wasn't the problem. But here, I don't have the density of the sodium chloride. And so I could look it up too, but it'd probably take me a long time to find it. So I'm not going to worry about it right now, because sometimes the amount of error that's introduced is small versus the amount of time it would take to find that particular information. It depends on the accuracy. If you're doing highly accurate work, then you probably should measure the density or look it up in a table. You could look it up in a table like the CRC handbook, but the CRC handbook requires a paid subscription, but it's quite useful to have when you need it. So what we're going to do is we're going to make an assumption. We're going to assume that the concentration, you know, it's going to be salty, but it's not like, you know, it's not like seawater. You know, the concentration of salts in seawater is very high. You know, this is going to taste a little salty, and it's going to light up the light bulb, but not as bright as, let's say, seawater. Although it's going to be kind of bright. And so what we're going to do is we're going to assume a density of 1.00 grams per milliliter. It should actually be higher than pure water. The reason why the density should be higher is because you got sodium ions and chloride ions in there, and those are heavy. You know, heavier than water molecules. Water molecules just weigh 18 U. You know, sodium ions weigh about 23, and chloride ions weigh about 35.5 U. And so we expect the density to be a little bit higher than this, but I don't know what it is. So the first assumption is this. We assume, did they tell us what the density is in the book, in the lab manual? If they told us the density, then let's use that.
It just says assume the mixture forms 100 grams of solution.
Okay. So there's basically what that's saying is assume it's the same density as pure water. And so, what kind of error would that? Do you know what the density of ocean water is? About close 1.03. So 1.03 is 3%. You know, if we assume that ocean water were the same as pure water, then we'd have a 3% error right there. And 1 molar is going to be a lot less, so our error should be kind of small, hopefully. This is like maybe 1% error or less. Considering how much time it would save, it's probably worth it, you know, rather than searching for it online. And then once you search for it online, you know, how reliable is that? Anyway, it's probably okay, because who would be posting these things on there anyway? All right, let's go on to the next assumption that we're going to make. You know what the next assumption we're going to make is? We're going to assume that the specific heat, I'd have to go online or look in the CRC for the specific heat of sodium chloride salt water. And I can find it. There are tables of specific heat of salt water. But in an effort to save time and hopefully the error is small, we're going to assume what?
A specific heat of water.
Yeah, we're going to assume that the specific heat of the salt water is the same as pure water. 4.18 joules per gram degree C. So we make these assumptions here, but what you want to do is you want to verify the assumption, because if you go ahead and do this, like in a scientific paper or at a scientific talk, If you go to scientific talk and you say, well, I'm going to go ahead and assume this, somebody's going to ask you, you know, what kind of error does that introduce into your calculation? You know, how valid is that assumption? And so even though, okay, you might say, oh, my teacher told me, you know, that's okay, but that's not going to really be satisfactory. So you want to look at it yourself to make sure, you know, if you're presenting. But I'll just tell you the error is small. It should be less than 1%. All right, next we need our delta T. Our delta T will be T final, which is the mix, minus T initial. This we get from the graph, you know, at 6 minutes. At 6 minutes. All right, not only is the salt water going to warm up, but what else is going to warm up? The calorimeter. And so let's figure out how much heat the calorimeter is going to absorb. And so we only have one calorimeter, and so it's going to be the specific heat of the calorimeter. Actually, I shouldn't call this the specific heat, because the specific heat is per gram, and we're not going to weigh the calorimeter. And so this is what we call the heat capacity of the calorimeter. This is from part 1. Times our delta T. Our delta T is going to be exactly the same, T final minus T initial. There's no delta T for the reaction. The reaction starts at T initial, and then eventually it'll go back down to T initial. So eventually this cooling curve will hit T initial again, and all the heat's been released. And so what we're doing is we're back extrapolating the entire cooling curve to see what that heat would have been, you know, if we all dumped it all at once, you know, and it didn't dissipate like it did. All right, so what are we solving for here? What we're solving for is, okay, we know these numbers. We know this from earlier. We know everything. You know what? The only thing we don't know is this, delta U. We know the amount of reaction. The amount of reaction is 50 millimoles is 0.0500 moles of reaction. And so what we're going to do is we're going to get delta U in terms of joules per mole. We can convert that to kilojoules per mole if it's more convenient, but we're going to solve for this. Okay, what was the next?
Solid sodium hydroxide and water.
Solid sodium hydroxide and water. Are we taking hot sodium hydroxide and putting it into cold water, and the hot sodium hydroxide cools down and the cold water warms up? No.
This is reaction based.
Yeah, this is a reaction-based thing again. And it's not a chemical reaction, this is a physical process. So we're taking solid sodium hydroxide and then dissolving that in water. When we dissolve that in water, so you just got plenty of water, dissolve that in water, we're going to get sodium hydroxide aqueous. It turns out that this is exothermic, and that is we're going to get energy here in this, what we call dissolution of sodium hydroxide, or dissolving of sodium hydroxide. The dissolution.
That water is our catalyst for this reaction. Because it's what's dissolving.
Yeah, yeah.
But we could use something else.
Right. We could just use, well,
Let's use a hydrocarbon.
hydrocarbons won't work very effectively. You need something polar. So sodium hydroxide could dissolve in some alcohols, probably not as much. So, you know, something that's polar that can tug on the ions to tear apart the lattice. And so our system's going to be this. Q the system is going to equal Q the process in this case. And the process is the process of dissolving or dissolution. So the dissolution process, I'll call it. And that's going to equal, well, when it's not an object, objects cool down and warm up. So sodium hydroxide is not an object, it's going to be a process. So when that's the case, it depends on the amount of sodium hydroxide. So how much sodium hydroxide did you use for this?
Oh, I have
Well, it's different for each party. It's like x.xx grams, right?
yes,
Yeah.
I had 2.
Or Z, I don't know how many moles. That would be less than a mole. So it's probably 0.zz moles, something like that. And so we can either get the energy, you know, in terms of joules or kilojoules per gram, or joules or kilojoules per mole. We could use any amount there, whatever is more convenient. And so what is that energy going to warm up? Well, how much water did you dissolve it in? 50 milliliters. So when you dissolve that sodium hydroxide, this is the weird thing. When you dissolve that sodium hydroxide in the water, does the volume change much? No.
Not enough to
Yeah, not enough to worry about. And so we end up with 50.0 milliliters of sodium hydroxide aqueous. All right, so we'll do an energy level diagram here, I think, as well. Let's do that. So in this process, we're going from higher internal energy to lower internal energy. And so we start off with sodium hydroxide, solid, plus H2O, liquid. This is going to be x.xx grams. This is going to be 50.0 milliliters here. And then when you mix those together, it forms NaOH aqueous. This should be 50.0 milliliters. However, how many grams is it? Even though the volume is,
say it would be perfect.
would it be 50 grams?
It could be if we assumed density of pure water, but this is no longer pure water.
No.
We're adding NaOH solid into it. It becomes a mixture.
Yeah.
You could assume slightly higher than no pure water, like 1.001.
Yeah, even though it's 50.0 milliliters, actually we can do better than that. You know how we can do this?
How?
This consists of 50, how many grams of water is that?
50.
That's, okay, so this is going to be 50.0 grams of H2O,
Yeah.
plus how many grams of sodium hydroxide?
2.
About 2, so x.xx grams of sodium hydroxide. And so the masses are additive. The volumes aren't necessarily additive, but the masses, you know, we had Le Chatelier's, not Le Chatelier's, Lavoisier's conservation of mass. And so this actually weighs 50x.xx grams of sodium hydroxide solution. That's what we have there. And so, so we don't need to know the density for this. We know how many grams we have. This is a little bit more concentrated than the sodium hydroxide solution that we used in the previous one. You know, because in the previous one we assumed the density is 1. In this case, the density is going to be closer to, well, let's say it's 52. That's going to be 104. This is going to be closer to 1.04. You know, more than the seawater. Which would be like a 4% error. It would be a 4% error if we assumed it's pure water. And so we don't want to assume it's pure water in this case. And so Q of the system here, which is equal to Q of the dissolution process, which is equal to the amount times delta U of dissolution. is going to equal minus Q of the surroundings. And so all the heat that's generated, all the energy is going to be absorbed by, okay, once the system's gone, once I've dissolved all this, the system's gone. What's left over? What's left over is the surroundings. The surroundings will be consisting of Q of the sodium hydroxide solution, NaOH aqueous, plus Q of the calorimeter, because the coffee cup will also warm up. Okay, so that will be over here. So we're going to start off with, okay, initially this is the, we're going to have a graph like this. Initially, the water is at room temperature or close to it. And then then the sodium hydroxide we're going to assume is at the same temperature. We didn't measure the temperature of the sodium hydroxide, but we'll just assume it's at room temperature as well. And so we're going to call that at T initial. Both of these will be at T initial. And then it's going to warm up. But sodium hydroxide is a little sluggish to dissolve, so we'll wait until we get a nice cooling trend out here, and then back extrapolate that to 6 minutes here. And so again, we're going to do 6 minutes here to determine the temperature of the final temperature. Excuse me. We call T final here, and the initial temperature T initial here. This is 6 minutes. All right, so eventually this is going to cool all the way back down to T initial. And so what we're going to do is we didn't collect all the data, but we have enough data here that we can back extrapolate to, you know, what would it have been had we mixed it in one instant of time. You know, if we could have mixed it. You know, what we have here is incomplete mixing. Here we have a little cold spot. Here we have a little hot spot. And so it's not completely homogeneous, the temperature in the mixture. But nonetheless, this is going to be at T initial, and then we're going to let this cool back down to T initial all the way down here, and then we'll back extrapolate how much heat was absorbed by the surroundings. How much heat was absorbed by the surroundings we can calculate from here based on the temperature increase of the surroundings. And so we're going to have 50x.xx grams of sodium hydroxide aqueous plus the calorimeter at T initial. And then this is going to absorb all this heat, and then we're going to get to this. We're going to have 50x.xx grams of sodium hydroxide aqueous plus calorimeter at T final. So continuing this, the sodium hydroxide, we have a problem here. I know the amount, 50x.xx grams of sodium hydroxide, whatever the stockroom gave you. But I don't know the specific heat. Now, in the last problem, we assumed the specific heat was the same as water. But it turns out this is going to be a bit more concentrated than the last one. But it's going to take too much time to look it up. Right, and so instead, what are we going to do? We're going to do this, but this is going to introduce a larger error. Maybe 4%, something, or maybe more or less, depending on, you know, when you put the salt in the water, how much it changes the specific heat. And so, joules per gram degree C. And so here we assume it's the same as water. This is going to definitely introduce an error here. If we wanted to do more accurate work, we probably wouldn't use coffee cups. We'd probably use more expensive, better insulated reaction vessels. But it's all right. Assume it is the same as water. And then it's T final minus T initial here. And so that's how much heat was absorbed by the sodium hydroxide solution, aqueous, not the sodium hydroxide solid. The solid is not an object. The solid is part of the process. plus Q, the calorimeter. We only have one calorimeter, so it's just going to be C of the calorimeter times delta T, which is T final minus T initial. The calorimeter started off at the same temperature as the solution and ended up at the same temperature as the solution here. And so we have these temperatures we get from the graph. We have the X values we got from the stockroom. The only thing we're missing is this, delta U of dissolution. How much energy is that? And normally, it could be extensive, you know, this whatever heat we calculated here was how much it was for x.xx grams. Or we could do it in joules per gram or joules per mole by dividing by the amount. So we take the heat divided by the amount, that gives us an intensive representation of delta U. And you're going to do both, joules or kilojoules per gram and joules or kilojoules per mole. Okay. What was the last one we did?
Solid sodium hydroxide plus HCl.
Yeah. So we did solid sodium hydroxide plus HCl. So this is going to be HCl aqueous plus NaOH solid. This should give more energy than HCl aqueous and NaOH aqueous, because dissolution of NaOH is exothermic in itself. And then we have the reaction, and so we should get more energy from this. But the products will be the same. It's just going to be sodium chloride. The product won't be the same as this. The product will be the same as the earlier reaction we did, which is aqueous sodium chloride plus water. So we're going to assume that the solid sodium hydroxide is the same temperature as the HCl. And so we're only going to have one temperature here. This is the temperature of the HCl solution. And then we extrapolate that out to 6 minutes to get the T cold or T initial. T initial. And then we dissolve the sodium hydroxide, that releases energy, and then the sodium hydroxide reacts with HCl, that also releases energy. And so the temperature is going to increase. But initially, it might not be well mixed. And so we'll wait for a nice cooling curve or cooling trend here. And then we'll back extrapolate this out over here. So here we hit a little cold spot here, but there's a little hot spot. Actually, this cooling curve doesn't meet right. Something like that, or you know, vice versa, something like that. So we ignore these initial points because we might not have it well mixed, and we focus on the latter points here to go back to where it should have been had we mixed it in one instant of time. If we could have mixed it in one instant of time, it'd pop up here and then start cooling down gently. So we'll back extrapolate this to there. So in this case, you know, the volume did change a little bit, but the volume change is so small. You know, because sodium hydroxide, 1 gram is about 1 milliliter's worth of volume. If we assume it's about 2 grams per milliliter. Oh, it is 2 grams. We're getting about 2 grams, so it's about a milliliter of volume. That's going to lead to about a % error, or 2% error. In the volume, but in terms of the amount of energy, in terms of work, it's not so significant. So again, we're just going to do this. We're going to assume that all this, there's no work, all this energy is in the form of heat. So Q of the system is going to be Q of the reaction. And Q of the reaction is equal to the amount of reaction times delta U. Of the reaction. This is very important because if there were a change in volume, do you know I can't use delta U? If there's a change in volume, I shouldn't be using delta U. I should be using another one. What was that other one?
Delta H.
Delta H, right?
What is it called again?
Enthalpy, rather than internal energy. In this case, when there's no change in volume or there's negligible change in volume, then delta U and delta H are the same thing. Okay, so continuing on here, the reaction we're looking at is going to be HCl. It's going to be at higher chemical potential energy, HCl aqueous plus NaOH. So what is the amount of reaction that I have here? In order to figure out the amount of reaction, I need to determine what my LR is. What is the limiting reagent? Is the NaOH the limiting reagent again, or the HCl now the limiting reagent? And so the amount of reaction depends on how many moles of limiting reagent react.
NaOH is still our limiting reagent.
Yeah, NaOH is about 40 grams per mole. And so it turns out that this is still our LR. You're probably going to get a different amount. We'll just call it Y.YY grams, something like that, of NaOH. We could do a calculation to verify that it is indeed still our limiting reagent, just to prove it to ourselves. And then it's going to form, so we should have a little bit of excess HCl left over, which can impact things like specific heat, but really very marginally. A little bit of in fact, I'm not even going to write it. Sorry, I wrote it down. There's going to be a little excess reagent left over, but I'm going to completely ignore it. And I'm going to say the product is going to be NaCl plus water. And not worry about that little bit of HCl that's left over. I certainly don't want to start searching tables for an HCl plus sodium chloride mixture. You know, what's the specific heat of that? Start to get quite involved. Okay, this is going to equal, you know, all that energy that was lost here goes into heating up what's left over after the reaction's taken place. So after the reaction's taken place, what's left over is the salt water solution here. So I have my salt water solution here. And the calorimeter. I'm going to warm that up as well. So the HCl and the NaOH were at T initial. The salt water, we're going to wait until the product cools back down. We're not literally going to wait until this hits T initial again, because you know what we're going to do is we're just back extrapolating it anyway. And the salt water and the calorimeter will be at T initial, and these are going to warm up to T final here. And so I'll have my salt water and calorimeter at T final. Okay, this will be my surroundings. So this is Q of the system is equal to minus Q of the surroundings, which is equal to minus, okay, the surroundings is going to consist of the salt water. How much salt water are we going to have? We're going to have 50y.yy grams of salt water. Actually, I forgot to do one thing, sorry. This is going to equal Q of the salt water plus Q of the calorimeter. I jumped ahead one step. And this is going to equal minus 50y.yy grams. Okay, again, we don't have the specific heat of the salt water, and I'm not going to look it up, so we're just going to assume it's the same. 4.18 joules per gram degree C. And our delta T here would be T final minus T initial. Okay, not only is the salt water going to absorb heat, but the calorimeter is going to absorb heat as well. So we'll have C of the calorimeter, we calculated earlier, times T final minus T initial. That'll tell us how much heat the calorimeter absorbed as well. Okay, and we have everything. The only unknown here is delta U of reaction. So we're going to solve for delta U of reaction. First, we're going to solve for extensive, that is how many joules of heat, and then we're going to get it into ratio. The ratio would be joules per gram and joules per mole by dividing by the amount. Okay. All right, any questions on this? So today we're doing the vacuum filtration, so you're going to have to set this up. If you need any help, let me know. But go ahead and check out the equipment from the stock room, and we'll go ahead and filter